Morning. Hi, everyone.
Morning.
I think we can start. I'm going to share my screen. Yesterday, actually, Monday evening, we finished this webinar with micromodeling of Masonry. Then we started talking about how to model Masonry. I showed you how to do micromodeling for a two-dimensional analysis of in-plane behavior of Masonry. And I also show you how to do the same with homogeneous macromodeling, using this kind of orthotropic mapper. Now today I will go and tell you about how to do the same with the out-of-plane behavior of Masonry. For the same reason, I will use a slightly larger model, so I will take advantage of this just to explain you how to give you an introduction to the parallel version of OpenSees, how to perform parallel computing with OpenSees and STKO. So I will first start by telling you, someone is asking, the content of the last lecture is not available on the website. Yes, because we finished this night actually decoding the videos. It took more time than what we expected, because there are a lot of hours of video. So today they will be online, and probably tomorrow or the day after tomorrow, you will find also these recordings here. Okay, so let me first give you a brief introduction to the parallel version of OpenSees. So I assume you are familiar with OpenSees, but probably not too much with the parallel versions of OpenSees. So I'm not going to talk about parallelism in general. I will just talk about the parallel version of OpenSees, because probably most of you have been using the sequential version of OpenSees, the one that you can download from the website. Sequential means that you can run your analysis taking advantage of just one processor. But since nowadays you may have multiple processors, or each processor can have multiple threads, basically you don't take advantage of the full power of your computer or your workstation. OpenSees fortunately has two versions for parallel computing, and if you want to know something about it, you can just write OpenSees parallel on Google and you will find all the answers here. So here you have a general overview with the links to download these two versions. Actually, up to 1 year ago, they used to distribute these two versions compiled. Now they don't distribute it, so you have to download the source code and compile it. Or you can use the OpenSeesMP that you downloaded the day on Monday. So basically here they give you a brief introduction about the parallel version of OpenSees. And here you can see that they have two versions, OpenSeesSP, which is for performing analysis of very large models, and OpenSeesMP, which is for performing parameter studies or analysis of large models with user-defined partitions. Why? This one is only used for like one single analysis of one large model. This one has multiple meanings. It can be used for many small models if you want to do parametric analysis, or you can use it as the OpenSeesMP. And this is what we're going to do today. So what is the main difference? Well, here you have, for those of you who are interested in programming, there is a link, is the second one, Introduction to OpenSees Parallel Classes and Applications. This one is interesting only for people contributing to the code of OpenSees. So if you're interested, you can have a look here. And they explain you how the parallel implementation in OpenSees has been developed. Otherwise, if you want to know something about the two versions of OpenSees, OpenSeesSP and OpenSeesMP, of course, you can find the links here, OpenSeesSP and MP. This one is the presentation of OpenSeesSP. As you have seen in this very brief explanation, it is done for performing analysis of very large model. What does it mean? Well, basically, with OpenSeesSP, you can use the same tcl file you use for the sequential OpenSees version. You just have few different commands, namely the system, where you have access to more advanced system of equations, solvers of system of equations. And basically, everything is constructed on a single processor as usual. But the first time you run the command analysis, everything is partitioned directly in OpenSees to different processors. So you build everything on processor 0 using a standard script, and OpenSees takes care of dividing this domain in small pieces, and it will send each piece to each processor, and then it will run parallel analysis, of course. Now, this is pretty easy for the user because the Tcl script is the same, as I told you. You just have to change the name of the linear solver. Then you can run large model, but the main problem is that it is not so efficient. For example, here they tell about this scalability issues. This application does not scale well because you have to create everything in a single processor. Now, if your model is large but not extremely large, this is fine. But if you have a very large model, it probably will fill that processor, and so you will not be able to partition it and send it to the other processes. So there is a certain limit to this. And then there is another limit that here is not explained, but basically, if you want to use OpenSeesMP, be prepared that some of the material model available in OpenSees or some of the elements will not work with the OpenSeesMP because the developer need to implement some kind of functions, and not all of them have been implemented. All of these problems are not present in the OpenSeesMP. That's why we are going to use OpenSeesMP. OpenSeesMP. So what is the difference between OpenSeesMP and OpenSeesMP? The difference is that in OpenSeesMP, everything should be written directly on the different processors. So there is no problem of filling one processor and then waiting for OpenSees to send the pieces to the other processes. But then there is a problem from the user point of view, because the user needs to write parallel scripts. What does it mean? Let me show you a simple example here. So you need to know something about parallelism, of course. So how to send messages to one process to the other. And this is already quite complicated for people that are not familiar with parallel computing. But then you need to create your Tcl file, not in the standard way as you are used to with OpenSees. You need to create it directly partitioned. For example, this is a simple example saying, okay, I have 3 elements, 4 nodes, and 2 processes. How do I write a parallel script for this? So in this example, he said, okay, if I am on processor 0, I will create node 1, node 4, and then the trust in between them. If I am in the second process, I will create the other nodes and the other elements. And the common nodes should be in both processes. Now you understand that writing this thing by hand, as you have done with this sequential version of OpenSees, is not easy at all. It's very complicated. That's why people often don't use this one for running large analysis. They only use OpenSeesMP for parametric analysis. And then we came with STKO. So what's the advantage of having STKO in this case? In STKO, we said, okay, we want to use OpenSeesMP because it does not have all the limitation of OpenSeesMP. But of course, the user is not able to write this kind of file. So we said something different. So we said, okay, why don't we implement the partition ourselves in STKO? And this is what we've done. So basically, we do what OpenSeesMP does at the beginning. So when you are done with your mesh, and you will see it in this example, you build your mesh. After that, you partition it, and you decide how many partitions you want to use. For example, in this computer, I have one processor with 8 threads. And then you go partition, you say, okay, tell me the number of partitions. Then you do partition, done. You can have a look at more or less how many elements and nodes you have on each partition. The partitioning is done with an algorithm that does everything in an optimized way, just to balance the load in the different processes. And the nice thing about this is that when you write this file, STKO will directly write the partition file, as in this example. So it will write the proper node on their parent process. For example, let me show you this one. If I open the node Tcl file generated by STKO, you can find this. Instead of writing directly the nodes, it says, okay, if I am on process 0, write those nodes. Then if I am on process, well, here obviously I have a lot of nodes, but you can find all the if else statement. If I am on process 1, then do all the other things, okay? So this is the main advantage. You are able to use OpenSeesMP, which does not have scalability issues and does not have issues of implementation. And you can have access to this parallel script directly because you do through a user interface. Okay. So this is a very brief overview of the parallel versions of OpenSees. If you are more interested and you want to develop code for OpenSees, of course, refer to this. Sorry, to this one. I just gave you an introduction about what are the parallel capabilities of OpenSees. So now coming to our example, here I will show you how to do micro modeling of a Masonry structure. And I took this example from a work of Griffith out of plane flexural strength of unreinforced Masonry buildings. And I will send you the reference. Yeah, clay brick Masonry walls. So in this experimental test, basically they tested a lot of walls with different shape ratios, with the presence or not of holes, different set of boundary conditions, and different levels of precompression. Now, for the sake of simplicity, we're going to do only the first wall, which is basically clamped in all the sides. Then they did two analyses, one with a certain precompression and one with no precompression, just to show that with a higher precompression you have a higher strength, of course. We are going to analyze this one, okay? So here you can find all the details about the experimental test, some details about the brick unit. There is not so much about the microscopic material properties. You have something about the brick, and then you have homogenized parameters for the entire masonry wall. Then actually, when I studied first this wall, I did some tests to understand what were the parameters for the mortar. Then they give you the typical mortar type, so you can find some reference values. Then you have all the details for the boundary condition. In this case, it is very important to model properly all the boundary conditions, and I will show you step by step. So basically, everything is applied. The vertical load is applied on top of this. The top vertical, the top part of the wall is constrained to go downward of the same amount. Then the vertical displacement will be fixed before running the pushover analysis. Then one difference that you will see here from the previous examples, because on Monday, all the examples that I've done were we're using load control analysis with an applied displacement. And that was fine because I had the application point was just one point. So it is the same if I apply a load and I do a displacement control, or if I apply displacement and I do a load control. Now in this case, it is different because there is no just one point of application. The entire wall is subject to a uniform pressure, to a uniform out-of-plane pressure. So I cannot use the same concept. I cannot apply a displacement. I need to apply uniform pressure, and then I need to do a displacement control, and in this case, controlling the deflection of the center point of the wall. So I will show you how to do displacement control analysis, and then I will first do it in the sequential version of OpenSees. I will show you more or less how much it takes in terms of time, and then I will show you how to convert this model in the parallel version. It will be very easy. Let me see if there is something else. Then we'll show you how to do the macro modeling, of course. Yeah, and these are the results. We are going to simulate this one. Then I will also take advantage of explaining you how to create some simple scripts to monitor the analysis, to monitor the pushover curve during the analysis. For example, here you will see how to create a plot for GNU plot, so that during the analysis you can see the graphs updating. So of course you can use many other plot techniques, but here I'm using GNU plot. So if you're interested, you can download it from here. It is open source, GNU plot. You go on the home page and then on download. And you can download one of these two for Windows, okay? And I already provide you with these simple scripts that basically goes into the graph folder and plots the experimental curve and the micromodel curve that will be updating step by step during the analysis, okay? So we can monitor if everything is going good. Okay, so let's start. So let me first create another folder. This one will be the folder that I will send you. And I need to copy this one. I need to copy the plot that you will find there. Then the basic drawing is a basic drawing that we use to import. And a custom script. It is where I will show you how to create this custom script for the analysis. I think it's all here. I have the reference. Okay, this is what you will find, plus of course the complete input file. Of course, you will not have this file here. It will be generated by the analysis. So I will remove this, and you will have this one, just the experimental test. Okay, so I don't have anything in the post processor. It is clean, and I'm going to create a new file. So the first thing that we're going to do is to import a basic drawing that I've done for the bricks, because I don't remember the dimensions, so I prefer to create, actually it is not this one. D2, okay, it's this. Okay, so just to speed up the modeling, I created a CAD drawing for the brick, and I will show you how to, when you have a regular brick pattern, how to do this micromodeling quite fast. And then I draw the basic lines for the dimension of the entire wall. It is more or less 5 meters times 2 point something, and then ½ meter in this direction for the turning walls. Okay, so when you have as we've done yesterday, Monday, when you have a basic drawing like this and you want to create planar faces out of it, you have the planar face command. Select all the lines that you want to use as boundaries of your face element, right click, and then the selected lines are still there and you can get rid of them by pressing cancel. Okay, so just now I have just this one. Now we can go in front of it. Why did I start with a basic drawing like this? Because now I can go on property. Now, without taking care about the properties now, I will just create 2 properties without specifying the material property. I just need to assign them in such a way that when I will copy this pattern all around, the material assignment will remain there. Otherwise, it will be very complicated when I fill the entire micromodeling and then I have to start assigning material properties. It will take a lot of time. So it's easier if you do something like this. You create 2 properties and then you will play with them. But brick shell, I just select this section layer shell because we are going to do a nonlinear analysis. But for the moment, I don't put anything here. I just need to create a clone, and I do the same for the mortar. Okay, let's assign some nice color because here it's important to see the differences between the two. Okay, this is fine for brick. And let's put some yellow for the mortar. Okay. Okay, so you go on sub-selection because we need to assign material to the sub-entities. So you switch this off and you keep only the selection of faces. And I think here it was, yeah, this one, and this one. And these are bricks. So I drag and drop the brick shell. And then these 10 centimeter layers are for mortar. And then I drag and drop the mortar. Once again, what is the reason why I took this extension of the lines? It's just because I want to create regular 4 nodes faces in such a way that I can use a structured mesh. Okay. you're not obliged to do this, but for this example, it is important because the shell element that we need is only 4 nodes in OpenSees. There is a 3-node shell element in OpenSees, but I will show you at the end of this video that there is a huge difference between a thin shell and a thick shell for a micro model. Okay, I don't want to anticipate anything, but keep in mind that you have to do a model now that is able to be structured in a mesh, should be meshed in a structured fashion. Okay. So basically now, once we have all the material assigned, and we will take care about the constitutive properties later on, we can start copying these all around. Okay, so for example, I will need to copy this one on the other direction. Now let me see the total dimension of this one because I don't remember. So if you want to query the dimension of a geometry, you can go here, query geometry, then you have properties, and then I select these lines here, and then I ask for query length, and the cumulative length is 240. So now I can select this one and copy paste it all around. We can use the ortho command, and so we can start typing 240, 240. And we'll do this first strip, and then we'll copy it on the other side. Of course, in this model, we could have been using the symmetry property, but I just want to use a larger model for showing you the performance of the parallel computing. Of course, this one could have been done just using the symmetry. Okay, so here we have our drawing. We need to get rid of the last layer here of faces because we don't need to repeat them. So I go in sub-selection, I select all the faces and cancel. Okay, I think we have a question. Okay. Oh, of course, now I'm showing you the standard way of creating this geometry, but we are working actually on an algorithm to automatically create the micro model out of an homogeneous surface. It is not ready now, so I will not talk too much about it, but we are planning to introduce it in the next version of STKO. Okay, so basically now we have this first strip, and as you can see, if I switch off points and lines, well, actually I made it wrong here. This one should have been, let me go on the front view. Okay, just before drawing it, I accidentally assigned the mortar here. Instead, it should have been just brick, so I will correct it. That's why it is important to pay attention at the beginning, which is something that I didn't do. Fortunately, I realized it just now, otherwise it would have been a mess. Okay. Drag and drop the brick shell. Okay, now it is fine. Perfectly. Now that we have this first layer, we can join it into a single geometry, because here, as I've told you yesterday, if you keep separated geometry, the mesh will be separated. So, of course, you don't want this. So I go back to the full selection, I select all these faces, but not the construction lines. And then I do sew faces. You can either go to the geometry and click sew faces. There is a command here, sew faces. Or you can directly type the command on the command line. Right click, and now all these faces are connected in a single one. The advantage is that if you go back on property and you look at the material, they are still assigned. That's why I prefer to assign everything on a single pattern and then copy it. Okay. Now, before copying it on the vertical direction, I want to take this one and rotate it from this side. Okay, so I take this, copy, from here to here, and then I rotate it, but without creating a copy. I just want to transform this geometry. 90 degrees, and we are fine. Now you have to make sure that these two coincide. Actually, I think they do not coincide. Okay, in fact, here I have the long part of the brick, so I should start with the small part of the brick here. So I have to cut these pieces. Yes, I have to get rid of the first layer. Okay, go back on face selection, and I get rid of these and this. Okay, cancel. Now I can go back to the full selection, and I can copy this one and move it close to the other. Not copy, sorry, just move. Okay, let's check it. Okay, so the long part of the brick with the short part and so on. And now I need to remove some parts here. Okay, these two and these two, so it fills by the end of the wall, and that's fine. And I can remove this one. Perfectly. Now I need to mirror this one. So I can select it, I go in geometry, select and mirror by creating a copy. Now I need to find the middle plane here. Well, I can use any other plane and then attach it. And then I can move this one from here to here. Perfect. And now I can simply drag and drop everything. Let me make sure here it is fine. Yes, it is. Okay. So now we do the same thing we've done before. We go in geometry, sew faces, and I select these three faces. Okay, and we're done. Actually, now that I'm, let me check if they are, okay, short with long brick, perfect. Okay, now that we have this one, we can just copy paste them along the height direction. So I can put the front view. I need to know what is the height of this wall. So once again, I go in geometry. I click on query geometry, and I want to know the height of this pattern. So I can simply copy it. So I select all the lines here and query length, and the cumulative length is 172. Okay, back on the front view, copy, 172. Okay, and we need to remove the last layer because the last layer was not using the, was in excess. Let me see, the last layer plus the last layer of mortar. Okay. So back to the front view, subface selection. So I can select only the subfaces, and I need to get rid of the last layer of bricks and mortar, just like this. And cancel. Okay. Now I go back to full selection. I want to make sure that I remove the proper one. Okay. Now I can select this construction line. I don't need it anymore. But actually I need it for doing just one extra thing. I will show you later on. But before doing this, I want to do a surfaces to attach all of them, okay? So I select everything. Oh, but let me first click on surfaces, and then I select all faces. Right click, and then everything will be merged into a single geometry. As you can see, now we have the attached surface with all the material property already there. Just do a quick check if everything is fine. Okay, it seems fine. Perfect. Okay, now that we have everything, I want to hide this one for a second. Okay, now basically we need to, since we are going to do a pushover analysis of this one, we need a control point. The control point should be in the middle, but if I show you everything, basically in the middle you have a mortar layer, a head joint, and I don't want to cut this one into pieces, okay, because I want to keep a regular mesh. So how can you do that? Now, of course, it is not so important. You can choose the nearest point for doing the pushover analysis, but I will take advantage of this to explain you how to create a particular constraint. So let's say I want to place a node right in between that mortar layer, and of course this node will not be attached to anything. So I will use an interaction to attach that node to the plane of the element it lies on. Okay. So to do this, I first hide this object. Then I want to draw a line in the middle. So from midpoint to midpoint, so that I can put a point in the middle here. Okay, so now I have a point here. This line is not useful anymore. Also this one. So I just need my face and my control point here. Okay, now I show everything, show all. You can see now that I have a point here in between. Perfect. Now I want to attach basically this point to this face using a kinematic interaction. So before assigning boundary condition, of course, I need to create an interaction here. So add, and we can call it control node tie. The control node will be the master. So click on the master. And of course, whenever you have two entities overlapping and you click on one of them, STKO will say, okay, but what do you want to select? In my case, I want to select the point here. Okay, this is my master. Right click, select the slave geometries, and I want to master it to this slave here. Right click. So basically now, if this point undergoes a rotation, this plane undergoes the same rotation and displacement, of course. There will be a rigid link connection. Okay, so now we have the entire geometry and the interaction. Just save the model. Okay, so here we have all the geometry. Now we can start creating physical properties. So we already assigned everything. So we just need now to create the three-dimensional constitutive models for bricks and shell, and then we will put it inside the shell section, which is already assigned. Okay. So let's create the brick property. Brick 3D, as we have done yesterday. We start with the 3D and then we convert it. Now in this example, I can tell you, and you can see from the experimental results, that there was no damage on the bricks. There are the failure pattern here somewhere. But I want to assign a nonlinear property also to the bricks, just because I want to show you what will happen if I use a wrong element, a wrong finite element, a wrong shell property. And if I use the wrong one, I will see that also the brick will break. Let me show you the failure patterns. Failure pattern we're going to obtain is this one. Okay. So let's start with a nonlinear brick. So ND plugin as the software damage 3D. And this was 52700 Young modulus. 0.15. Then we have 2, 0.05. 30 megapascal of elastic limiting compression, then 40, the peak strength, 10, the residual strength, 0.002, then the fractional energy that should be regularized, of course. Then we use a Rankine surface for tension. The default parameters here are fine. In this case, we don't need to use any plasticity. We're going to use a simple monotonic loading and the implex algorithm, so it will be faster. And of course, automatic fracture energy regularization. Okay. So this is for the brick. And we need to do the same for mortar. Mortar 3D. Model material ND. Plugin as the software damage TC3D. Now the mortar was 1000, 0.15, 0.1, 2, 2.5 peak strength, 1 residual, range of 10, then this one can be the default, ranking. Then I will show you this parameter here. I've been talking about this yesterday, then I will show you the reference once again. Which is this one. Okay, that model, that parameter basically controls the shape of the failure surface. If you remember, I told you that we have two. This one is a tension compression damage model, now coupled with plasticity, and it has two surfaces, one for compression and one for tension. Now in this case it was a lubliner, but we have the option to choose between lubliner or Rankine. Now the point is that the compressive surface, which is this one, has a parameter which is the M1, which is shear compression reduction factor, a parameter that goes from 0 to 1. When it is 0, basically the compressive surface will be a Drucker-Prager surface, and when it is 1, it goes to the lubliner surface. Now what happens is basically that since when we are in shear, we have two different eigenvalues, so both surfaces are active, both the tensile one and the compressive one. So basically, if the compressive one is larger, we will show, the model will show a higher latency. And there is an example here, simple example why in the damage model this happens. In plasticity is different. In plasticity, you explicitly impose the latency angle because you have a potential surface, so you can do that. But in damage model, you cannot. Fortunately, the tension compression damage model, since it has two surfaces, is not like the isotropic damage where the entire stress tensor is scaled by a single damage parameter. Here, the tensile part and the compressive part will be scaled according to their surfaces. So you can understand that if the compressive surface is larger than the tensile one, the damaging compression will somehow grow slower than the one in tension, resulting in a changing direction of this stress vector. And basically this results, for example, in this case, I'm loading it with a trial stress in pure shear, but after the damage, I am not only in pure shear, I have another compression here. And this one will be translated into the latency. Why am I talking about this? Because in this example, you will see that due to the boundary condition, because after we apply the vertical load, we will keep the top of the wall fixed at the current position. So basically, if you expect shear deformation to happen, you will see the latency. So if you have the latency, you will see some kind of precompression increase in strength because the wall cannot uplift. So this parameter will be very important, and the analysis will be very sensitive to this one. And in this case, I will use 0.5. Then I will show you what happens if we change this parameter. Because someone may say, okay, but here I have an out of plane failure, a bending failure, probably I don't have too much about shear. I don't have to take care about shear. You will see that here, shear at the microscopic level is the most relevant part. So this one is going to be important. As I said, I don't care about plasticity now, and we are going to use the implex algorithm and also automatic regularization. Okay, can save it. Now I have to put these two materials into my shells, okay? But actually in the previous examples, I told you that whenever you have a three-dimensional constitutive model, you have to use a converter, something that converts this 3D model into either a plane stress one for the 2D analysis or into a plate fiber one into a shell analysis. This was the general rule, but our constitutive model is able to change itself automatically, so you don't need to actually create that wrapper. I showed you that yesterday because that is the general way with all the OpenSees models, but some models in OpenSees, among which you can find our model, they can be converted automatically, so you don't need to specify the converter. Now, one problem here, we decided to create these two models after the shell because we assigned the shell before. Now, if I go onto the brick shell and I try to reference, for example, I want to create 5 layers of that three-dimensional material, I go here and I cannot find it. Why? Because in order, it has been created later on. So here the order is important. So I can just take this one and bring it up, and the same thing for mortar. So now the two shell sections are able to see them, okay? So now let's go to the shell. In this case, the total thickness of the wall is 110 millimeters. Here I use just the minimum amount of fibers that are useful for representing a good bending behavior. It should be 5. You can use more if you want, but 5 is already enough in this case. And all of them will be made of brick 3D for the brick shell. Of course, I have 5 layers, so I need to create 5 thicknesses of 21 millimeters each one. And same thing for the shell, for the mortar shell. Five layers of mortar. Oops. And 5 layers thicknesses. Okay. So we are now set with the material properties. I think we don't need any other material. Yes. Now we need to choose the finite element property, so the element property. Okay, I think oof, I have a problem in understanding Portuguese. So yes, I can understand it now. We have there will be the recording, so don't worry if you cannot attend the first part of the webinar. Today you will see on our website the recordings of the Monday's webinar, and by tomorrow or the day after tomorrow you will have the video for these ones. Okay, so now we have all the constitutive properties. As I said, physical properties means define the constitutive behavior of your model. Now we need to define the kinematics. For defining the kinematics, you need to specify the finite element properties. Now, in this case, we are going to use a single finite element for the entire model, okay? Because basically it's everything a shell here. And you can call it shell. Now we give you a simple introduction about the shells, because we have been using the shell in the webinar about the reinforced concrete shear wall. But there it was not so important because actually it was an analysis in plane. I decided to use the shell just to explain you how to do a three-dimensional analysis of that. So basically here we have the two main families are the DKG, Q and T. Q stands for quadrilateral and T for triangle. They are based on the Kirchhoff law theory for the plate bending part. On the contrary, the MITC 4, and 9, they are only for quadrilateral elements, 4 nodes or 9 nodes. And they are instead are based on the Reisner-Middlin, so the thick plate bending theory. So now then you have the nonlinear kinematic counterparts of them and the thermal, those for thermal analysis. But you will be using most of the times one of these three actually. The 9 node is almost never used. So one of these three. How do you choose between them? I typically tend to choose always the MITC. Why? Because it is thick, yes, but it can be used also for thin plate analysis because it is based on the MITC formulation, which stands for Mixed Interpolation of Tensorial Components. It's a formulation given, it's a quite standard formulation given many years ago by Butt and Dworkin. And you know that a thick shell formulation in the discretized finite element problem has an issue called transverse shear locking. It is not able to represent the solution properly when the problem is thin. You have a thin plate. The MITC instead does not have this problem. So let's say it is a general plate bending. Well, the DKG is based on the discrete Kirchhoff theory, so it is good for thin shells, but not for thick shells because they neglect transverse shear deformation. So here you may say, okay, but we know that this wall is 5 meters times 3 meters more or less, and the thickness is only 100 millimeters. So it can be safe to assume that it is thin, because someone may say, okay, a shell is thin if the ratio of the thickness over the characteristic length of the model is less than 1/10. And here it is. But then you will see a problem. Here, the characteristic length should not be the one of the dimensions. It should be different, and I will show you later on. So the good solution will be given by the shell MITC4, and then I will show you what happens if you choose instead the thin shell theory. Okay, shell, that's fine. I can select the entire geometry and drag and drop the shell. Just to make sure I assigned an element property. Yes, it is there. Perfect, we can save it. Okay, now we have all the element properties. We can go on the boundary conditions. Okay, now here we have to take care about all the boundary conditions. If you go here, here basically everything is explained, but all these sides are pinned. So we are going to simulate the same. Here it is easy to define boundary conditions, okay, not layer by layer, but direction by direction. So I will create first a fixed Z. It will be a constraint, a single point constraint, fixed. We are in 3 dimensions with 6 degrees of freedom. So UR, displacement plus rotations. And here I just want to fix the vertical displacement. And of course I have to do this to all the bottom lines. So I simply do a rubber band selection of all the, let me switch off the grid for a while. Okay, of all the bottom line. So all these nodes will be fixed in the Z direction. Then I need to find the nodes that are fixed in the Y direction. Okay, the 9 nodes it's more accurate basically, but I always never use it because it is more accurate. But in this case, we have many elements. So you will see basically no difference from the quadratic to the linear displacement, but it will take a lot more time in solving the system of equations because a 9 node will make a denser stiffness matrix. So I typically never use quadratic elements unless I have to do a model with very few elements and try to get a good response in terms of displacement. And second, this one is good when you do linear analysis because the stress is almost continuous, while in the discrete case, in the linear case, the stress is almost, you see high stress jumps. But in this case, in any way, you are going to use a very discontinuous nonlinear material model, so you will see stress jump anyway. And then you have sudden change of material properties from bricks and mortar. So taking advantage of this accuracy, I think, is not so important. I will more focus on performances. And then, of course, you have to take care about something else. In OpenSees, the characteristic length is given by the minimum size between the nodes. Now, this is fine for a 4-node because it will give me the full length of an element. A 9-node will give me half the length. But actually, in the 9-node element, the localization happens in a function of the total length, which is, I think, 18 over 30 or something like this, because it depends on the quadratic interpolation. So it is not so easy. I usually prefer, when I have to do with strain localization, I prefer to use simple models rather than complicated higher order interpolations. Okay, what else? So, oh, we fixed the X. Now we need to fix the Y, and the Y displacement, so displacement in this direction, of course, should be fixed in the turning walls and only in these horizontal lines here, because actually this one can actually slide, because there are U channels basically. So we're going to simulate this fact. Let me show you. As you can see, there are U channels everywhere. So that's why, for example, in this line, which is the vertical line of the turning wall, I don't fix the Z displacement, of course. The same thing, I don't fix the Y displacement here, and I don't fix the X displacement here. Okay, that's why we are proceeding component by component. And in this kind of example, it's very important to model boundary condition, otherwise you will not be able to see any good results. So fix Y, constraint, single point, fix 3D displacement rotation, Y, and I need to fix these two lines here, so I can drag and drop. I can select a rubber band selection here, these two vertical lines, as you can see here, and then I want to look in the YZ plane, so in the left plane, and I want to select all this line and all this line here. Okay, so all these lines here, you cannot see it because there is the symbol of the previous constraint, but all these lines should be fixed in the Y direction. So we have YZ. Let me check. Okay, I use the Z. Now we have to do the same for the X displacement. Fix X. (3D) displacement rotation X. And here we need to fix the X. Of course, here on the border of the turning walls, on the edge, vertical edge of the turning walls, because there is the C channel, and also on the bottom. We don't need to fix the X here because this one is free to slide, but it will not basically. So all this edge, then I go in the front view so that I can select all the corners like this. And this one. Let's check that I selected properly. Borders, vertical border is fine. Horizontal border and vertical border there, and also on the other side. Perfect. So press OK. And we have this last boundary condition. So these are the three fixes that we need. Then we need something else. I told you that, let me save this one. Now we need some kinematic constraints. As I told you, here we are going to apply a vertical load, but as given in the example, the vertical load is applied on a steel structure that makes the vertical displacement on the wall constant. So every point will displace it of the same amount. So we need a constraint that says, okay, I will apply a load on you, but you have to displace downward of the same amount. So it is an equal DOF constraint. So for an equal DOF constraint, we need a master and some slaves. So whenever you have to create this relationship between master and slaves, you need an interaction. So let's create another interaction. which is called eDof top z. And once again, we need to select master and slaves. Now, it is not important what is the master, because we are going to create an equal DOF. An equal DOF doesn't have anything to do with rotation. So it is not important what is the center of rotation, because there is no rotation there. But just for visual purposes, I will try to select the one in the middle. So it is nicer to see. Just one of them, for example, this one. Right click, and then all the other nodes are slaves. It is not important if I select once again the master node, because it will be automatically excluded by STKO in the selection. Okay, right click, and what I obtain is a representation of all these lines connecting the master to all the slave that I selected. Okay, now that we have this interaction, we go back in conditions, and I create a new condition which is called equal DOF of UZ. This time it is not a single point constraint, because it is a relationship between the DOF of one master node to the DOF of the other node. That's why it's called multi-point constraint. And it is an equal DOF. So I simply saying the degrees of freedom of the slave node will be equal to the one of the master node. So we are in 3D, displacement and rotation, and I want to tie together the vertical displacement, UZ. So I select this one and press OK. So we have this other boundary condition. Then we need a similar kinematic condition also for this node. As I told you, this is not part of the structure, but I just want to keep the exact control node at the center of the element for the displacement control analysis, but I don't want to cut and to distort my mesh. I just want to keep my mesh quadrilateral and put a node here. And of course, I need some tool to say, okay, this node should remain fixed onto the surface and move and bend as the surface bends. So this one can be created not with an equal DOF, because as I told you, an equal DOF has nothing to do with rotation, just displacements. Here we have the rigid link. So we go under model, constraint, still a multi-point constraint, and it is called rigid link. Now for rigid link, you have many options in OpenSees. First of all, you have to specify the dimension. In this case, we are in 3D. And then the model, it can be a bar, which is like an equal DOF, but instead of specifying each DOF one at a time, it will consider all the DOFs. But it will be only translational. Otherwise, the beam. So the rigid link with the beam option is a full rigid body, okay? But of course, this requires both master and slave nodes to have 6 degrees of freedom. This is our case because we are working with a shell. So we select this interaction and press OK. Okay, so we have also this other multi-point constraint. Let's save it. And now we need 2 boundary conditions for the loading. Let me see if I have everything. No, actually 3 boundary conditions for the loading, yes. Because first we are going, as I told you, now we have the constraint for saying that the top displacement will be equal in all the nodes. Then we need a vertical load. But before applying the vertical load, I need another constraint. At a certain point in my analysis, so after the vertical analysis, so I apply a vertical load, the wall will displace in the z direction of the same amount. Then before starting the horizontal analysis, they decided to keep the vertical displacement fixed at the current rotation, at the current displacement, okay? And then they will push the wall. So we need to reproduce this condition. And this can be done not with a fix, because it's a fixed boundary condition as we have done with the previous. They are fixed in absolute value. So if I put 0, it will be 0 of the undeformed configuration. So it will go back to 0. I don't want that. I want to keep it fixed at the current position. So I can call it fixed top at current u. And this can be done using a load, an imposed displacement, because in the imposed displacement, of course, we have to choose the dimension and degrees of freedom. We can say, okay, I want the UC fixed at 0, but not in absolute terms. We want to use a relative value. So it should be 0 at the time we apply this boundary condition. So if when we apply this boundary condition, one node will have a certain displacement, it will be fixed at that displacement plus this value, which is 0, of course. So fixed at the current displacement. And this will be applied to the entire top edge. So we need to select everything, but need to select this one, all the edges. Did I select it? Yes. But I don't have to select this. Okay, perfect. And press OK. So this one has been assigned to the entire edge. Of course, when you have many boundary conditions, you see that the colors pretty much are always the same. So you can, of course, you can change it. For example, here it is difficult to see the last constraint that I put. Of course, you can customize it. So you can go here, edit. First of all, whenever you edit, you can see the previous selection. So you can see it is there. If you want to make it more evident, you can go in the shader, for example, here, you can change the point color, and I want to make it red, for example. And you can make it larger. For example, point size, I can make it 12. You will see it differently, okay? So you can play with it. Now I will go slightly faster, but you can change all the appearance. So fix at the current displacement, then we need other two boundary conditions. The vertical load on top and the horizontal load on the surfaces. So let's go on condition, vertical load. We go under model, load, force, and we use the edge force. As I said yesterday, in OpenSees, if you know OpenSees, you don't have distributed forces on edge, faces, or volumes. But in STKO, you do. What does it mean? It is not an extra component that we added to OpenSees. It is just a tool that allows you to specify something that is distributed over a line or over a surface or over a volume. And STKO will take care of doing the nodal lumping for you. So ultimately, the output that you give to OpenSees will be the standard nodal load, concentrated force. So in this case, it was a uniform pressure of 0.1, I think. Let me see. It was a uniform pressure of 0.1 megapascals. So here the thickness is 110. So we need to put here minus 11. It should be already integrated over the thickness, okay? So 0.1 times the thickness of the shell. So here basically we have a force which is a distributed force which is force over length in minus z, okay? And I need to select all the edges on top. Okay, so I have my vertical load here. It is yellow, it cannot be seen very well, but we can change it, as I told you. We can change the edge color to green, for example. Okay, this is our vertical load. Now we have to do the same for the surface load, okay? So let's go on condition, add pressure, load, force, and phase force. Now, what value do we want to apply to this pressure? Well, actually, it is not important because the value that we assign here will just be a reference value because we are going to do a displacement control. So the displacement control analysis will take care of computing the load multiplier that multiplied to this reference load will push my control node to a certain displacement that I will specify. Now, typically, when I do a displacement control analysis, I used to put a load that integrated over my structure gives me a unit force. Why? Because in this way, I can go and read directly the load multiplier, which will be the total reaction force. So in this case, how do I put this pressure that multiplied by my surface will be 1? Well, I can go, before doing this, I go in geometry, I go on the top view, then I go on query geometry, I go on properties, I select all the front faces because I want to assign a pressure only on the front faces. Okay. Oops. Let me make sure I select all the only faces. Yes. So all the faces here and query area. It will give me the area of everything plus the cumulative area. So I can select it, copy, Control C, and then I want the area. So 1 divided by. Okay, so this is the value I have to apply as a pressure to have a uniform, to have an integrated force which is 1 over the entire structure. Okay, of course, you can use whatever you want and then extract the total reaction. But I will show you that in this case, it is much more convenient because I'm going to show you a script that you can easily get the data from OpenSees and plot it on a dynamic plot that you can update during the analysis. So unit pressure of 1 Newton integrated, and it will be a surface load force, face force. We select the entire faces, front faces only, sorry. Now it should be a pressure along the, oh, I selected edge force, sorry, that's why you're allowed to select only, so face force. Once again, I go on top, select all the faces, perfect. It will be along the positive Y because I have to push it in this direction. So I can put this value here. Okay, 9.89 to the minus 8. Okay, it is that. And press OK. So here you will have all your pressure load. Let me see what is missing. No, this is fine. We have the pressure load. Okay, now we can start with defining the analysis steps. So let's first save this model. We have a question. Oh, let me check. You're right, thank you. So Control X, 0, and positive Y, perfect. Thank you so much. So in the Y direction, perfect. Now we can start with the analysis steps. Okay, so now we will fill the analysis steps. We will have our mesh done. Then we can run the analysis in sequential version, and then we will go and take a coffee break. So you will see after how much does it take to finish this analysis for a sequential version, so just one thread. And then we will do the same with the parallel version to see if we have any improvement. So the first analysis will be the recorder. Recorders, MPCO recorder. We can call it results. And we want displacement, rotation, because it is nice to see the failure lines with the rotation jump. Reaction force, we need it if you want to post-process something or reactions. And then we want section force and section deformation if you want to plot the shell moments or shell deformation as for beams. So section force and deformation are the integrated stresses over the thickness for the shell or over the area for the beam. And then if you want to plot something at the Gauss, not the Gauss point level, but at the fiber level, it can be stress or strain tensor in every point of the shell. So you can inspect really what's going on inside each layer of the shell in terms of stresses. And if we want also the damage. So we use the same concept. We are asking for a value which is stored in each fiber of each Gauss point of the shell. So we write section, fiber, damage. Yes. Then, as I told you yesterday, we want to record everything. Otherwise, we can restrict the selection to a particular region. So this is fine, recorder. Second step, we add the primary boundary condition, those that should be there for the entire analysis. So add boundary condition, and those will be so pattern, add pattern, constraint pattern, and here we can put the three single point constraint, which is fix x, fix y, and fix z. So everything is properly fixed here. Then at this point, we also need to apply, since from the very beginning, we need to apply a multi-point constraint, actually two multi-point constraints. The equal DOF at the top, because in this first analysis steps, we have to push this wall down, but it has to move of the same amount. So equal DOF on top. And then of course we need to attach the control node to the surface, otherwise the matrix will be singular. So we introduce also the rigid link. Otherwise we have an hanging node and we will have a singular system. Okay, so boundary conditions are there. Now we need the vertical load. Add vertical load. We go in pattern, add pattern, load pattern. Oh, before doing this, of course, I always forget to create time series. So cancel. We go back to the time series, because before defining the loads, we always need time series. So we need, in this case, a linear one for applying the vertical load and for the displacement control. Okay, and we need a constant one for fixing this displacement at the current position. This is just a remark, I already told you yesterday, but fixing a node at the current position, you may say, well, but you don't need a time series because you're fixing something at 0. So whatever time series I assign, it is a number times 0, so it is always 0. No, because it is 0 plus the displacement at the current position, so it is a number. And if I apply a time series which is not constant, but it is linear, for example, it will not start from that position, it will start from 0 down to that position, and this is not what I want. I want to keep it that fixed. So I need a time series which is constant. So we can call it constant. Okay, so we have all the time series here. So the first load that we apply is the vertical load. So we create a pattern, add pattern, load pattern, and we choose the linear time series for the vertical load. Okay, and we are done. Then we need to apply, then we need to do the vertical analysis. We are fine for the vertical analysis, and then we do the rest. So vertical analysis. Vertical analysis, we go here, analysis command, we choose a static analysis with a penalty method, 1 to the power of 15, as yesterday. I told you how to more or less calibrate this value, if you remember. So you take the maximum value that you expect from your stiffness matrix. If you don't know, you can take the largest Young modulus that you have there. You take the order of magnitude. In our case is 50,000 for the Young modulus of brick, so the order of magnitude is 10. Then multiplied by the thickness, it has other 2 order of magnitudes. Plus you have to assign to this 8, 7 to 8. So the value should be around that. In this case, it is 1 to the power of 15 or 16 at most. If you assign a value which is too small, the constraint will not be applied correctly. If you assign a higher value, it may happen that the entire stiffness matrix becomes singular, because it is so high that all the other values will look like 0. So keep in mind, evaluate the order of magnitude of your largest stiffness in your model and add 8 to it. Okay. So in the first example, we are going to do it with sequential versions. So we leave the default number and the default system. We choose a Newton algorithm, a displacement increment test, because we cannot use the norm of the residual with the penalty method. This is fine. 10 iteration, actually we just need 2 iteration. I just want to print the iterations here. We do a load control, we just need 1 step. So 1 increment with the lambda 1, because with this vertical load we don't reach any nonlinear range. And then of course we want to keep the load constant after this analysis, and we want to reset the pseudo time step to 0. Okay. So this is our vertical analysis. Later we need to, after this analysis is finished, we need to keep the displacement of this top wall fixed at the current position. So we just need to add another load. So add fixed top. It is a pattern, load pattern. We need to add a load pattern with the time series constant for the reason I told you before. That constraint is a single point constraint. So we go here and we choose fixed top at current UZ in a constant way. Then we need to apply the uniform pressure, which is our horizontal load. So add horizontal load. As you can see, the steps are pretty similar to the others that we have seen on Monday. It is a pattern, a load pattern. Here the time series is not so important. You can either choose the linear or the constant one. It is not important because since this load will be controlled by the displacement control analysis, is the displacement control that computes the load multiplier for this. So you just need one of the time series because OpenSees needs it for its command. Otherwise, it will give you an error. But it is not important which time series it is in case you're doing a displacement control analysis. And the load is a phase force that will be converted to nodal forces, so it goes under load. And it should be this one, unit pressure, yes. Unit pressure. Remember that the value of the pressure we assign is such that the entire horizontal load is 1 Newton, so 1 unit. So we can read the entire reaction force through the load multiplier. Okay, this is fine, and now we need to create the displacement control analysis. So I can clone the vertical load and change something. Push over. Static penalty is fine, same number, same system. Newton, non-displacement is fine. I don't want to use the print flag because I'm going to print it in a different way. This time is not a load control, it is a displacement control. And when we will do the parallel version, we will go to the parallel displacement control, okay? So now, displacement control. Oh, for the displacement control, we need a selection set, but we don't have it. I forgot to create it. So I accept it, and then I will go and modify this one. We need a selection set that contains the node that we want to control. So this is pretty easy. I go in the selection set, I click add, then I select this node, select, right click, and then I give it a name, and I call it set control node. Okay, back to the pushover definition. Displacement control. The selection set for the control node is this one that we just created. The degree of freedom should be numbered from 1 to the end of, so 1 to 6. We want to control the y displacement, so it is 2. And the increment. Now in this example, the total displacement we want to achieve is 35 millimeters. So in this test, we are going to use just 100 steps. So we can just put here 0.35. Yes. Now this is, we don't need this one because this is the last analysis. Now, if we do this, it will run 100 steps directly. So we cannot do anything in between each step, okay? So this is the standard way for running an analysis in OpenSees. It will run 100 steps with this increment each one. The problem is that I cannot interact with the analysis. I cannot do anything while the analysis is running. So I can do something different. I define the increment here, and then I say, no, I don't want to perform any increment here. I set 0, And then the incrementation, I can do it manually later on. So I can do something between one increment and the other. In this case, I want, for example, I want to print some information to the screen, and I want to print a graph in such a way that this one can be monitored during the analysis, okay? So for doing this, as someone has asked yesterday, you can use a custom script. For the custom script, you go under miscellaneous command, custom script, and here you can put whatever you want if you know something about TCOL and something about OpenSees, of course. Now, don't worry about this because in this example, I already have something already prepared, and you can find it day 2, Masonry micro modeling out of plane custom script. You can copy paste it. And I'm going to show you what it is trying to do. So, well, of course, we first take the initial time and the end time so we can understand how many seconds have been spent in this analysis. Keep in mind, this script is made for parallel processing. In fact, we have the process ID variable. But in this case, I will first show you how to do this one in a single processor, so without the OpenSeesMP, and we will measure the time. So for this purpose, I create a set process ID equal to 0, because otherwise it will give me an error because the standard OpenSees doesn't have this variable set. So I set it to 0 because it is the only process that we have. And what I do, this is my total displacement. This is my number of increment. This is my increment. Then if I am on process 0, I will create a file in the graph directory, and I will start writing 0, 0. And then for each step, instead of saying, okay, analyze 100 steps, I say for each step, do a single analysis. If something goes wrong, just break the loop. If it is fine and I am on process 0, I want to print some information. I want to get the number of iterations from OpenSees. I want to get all the norms that I obtained during the iteration. I take the last norm, which is the norm that I accepted for convergence. And then I print the current increment, the number of iterations that it took to converge, the last norm, the percentage of the analysis. And then I write something on this file. Basically, I take the maximum displacement directly from the increment times the increment ID. Then I get the total reaction forces by the get time function. Now this get time is an OpenSees function that gives me the current time step. So you may say, why are you taking the time step? Because in OpenSees, the time step in a static analysis in displacement control is a pseudo time step, is not a real time, and it is exactly equal to the load multiplier. But since my entire load was a unit load, this load multiplier is basically the entire reaction force, okay? So I can take this one, or actually it's the opposite of the entire reaction force, it is the total load applied. Now in the example, it was in kilopascal. Okay, so I take this one, I take the area, I convert it, then I obtain the pressure in kilopascal here. And then I write on this file, displacement, a tab, and this uniform pressure. Then since I want to update it every step, I need to do a flush. Otherwise, everything will be buffered and will be written to the file only when the operating system wants. Since I want to update it every time, at every step, I call a flush. Flush means put everything that was buffered inside the file. Then finally, I close the file here. That's all. It's not so complicated. It's just to show you how to interact with OpenSees. And this is one of the strength point of OpenSees, because whenever you want to do something, you can do it. And STKO allows you to do it through the custom script. Okay, so we can press OK here. We are almost done. We are going to do a coffee break in a while. Perfect. Now we can save it. We go in mesh, of course, because we didn't mesh anything up to now. For global seed, now to keep the timings quite small, I will use just one element for each geometry. Okay, it may seem too coarse, but you will see that the results will be very good because a macro model actually do not need a very fine discretization. Then the mortar. The element of the mortar will be quite distorted, but it is not important because in OpenSees, the kind of displacement that it has to deal with is not so complicated, and the characteristic length in OpenSees is taken not as the square root of the area, otherwise I will overestimate the amount of energy. It's taken as the minimum length, which is perfect for our purposes, because it will always be 10, okay? So for me, taking a mesh, which is this entire zone, is fine. So 1 by division, done. Then of course I need to assign the mesh controls, because by default I use unstructured triangular mesh. So I go on phases, and I want them to be structured and quadrilateral. So I go here and I select everything, assign, done. Okay, and then I can build the mesh. Okay, so this is my mesh. As you can see now, the constraint is perfectly meshed. So each point of the mesh is constrained to the master node. Same thing here. This one is constrained only to the 4 node of this element. And in the same way, all the distributed loads that you applied are actually discretized in the single nodes. Now I don't do any partition because I will use the sequential OpenSees. So I can save it. Now we'll run the analysis and see. Let me go back to OpenSees because I was using the OpenSeesMP before. I hope I wrote everything correctly. Let me see. Okay. As you can see, it doesn't take too much, but it takes some time. This is the first step, and then it is doing now the displacement control analysis. As you can see, it takes up, let's say, 10 seconds for each step. It will take a lot for running the entire analysis, but you will see that instead of going with parallel, it will take just 2 minutes.